talk because it's going to be slide talk, and this is really to just introduce some of the ideas of the last two chapters. And I'm not going to do any details. My goal is to sort of just show you some interesting examples and to make it clear there's still more stuff to learn when we're doing this toric geometry game. So the outline is I'm going to begin with something called the icosahedron. It's an example from chapter 15. Then we're going to time travel 240 years in the past and see some things that Bezout did that are pretty interesting. And then I'll talk about the general context of those two examples. That'll take a while to sort out. And there are polyhedra involved. And then I'm going to take one of our most basic examples, the one we saw on the first day, and just sort of think about this from the point of view of sort of geometric invariant theory. We're going to look at one other example, and then I'll finish off with the toric minimal model program. And like I say, it's about 100 pages of stuff, and so just hold on to your seats. And the answer is don't worry, there's no exercises. This is more just for fun. And so to start with, take a lattice hexagon. We've seen some very classic ones. And put it at height 1 of a cone. That's a construction we've done several times. But then we subdivide it. And so we, basically I pick you can think of triangulating the hexagon. So I get 1, 2, 3, 4 triangles. And the crucial thing is just to use disjoint diagonals. So I don't want them to cross. I don't want to introduce any new vertices or anything. And so it turns out you get a three-dimensional simplicial toric variety. And you can actually prove it's quasi-projective. And so then we play our usual game, and there's our favorite exact sequence that has, in 3 dimensions, so that also has rank 3. And so, and because it's simplicial, that means when I go up over the real numbers, I just get R3. And the quasi-projective means my Neff cone has dimension 3. So we have this nice 3-dimensional Neff cone. And remember, the interior is the stuff that is sort of ample stuff. And so we're in pretty good shape there. And but now comes the fact that there's more than one way to triangulate this. So what does that imply? Well, so let's take a different triangulation. I'll get a different toric variety. I'll call it X sigma prime. But they'll have the same rays, because after all, the rays are just these 6 the 6 vertices of the hexagon. And so and the rays determine the class group, and so that means that I'm still going to get this. So in fact, I have 2 different toric varieties, but their Neff cones live in the same space. So that's pretty interesting. And it turns out in this case there are 14 triangulations. I'll show you all 14 in about a minute. And it turns out there's a lot of combinatorics lurking here. It turns out that if you have a polygon with n sides and you want to count how many ways can you draw diagonals to triangulate, basically it's given by a Catalan number. And in this case it's always the Catalan number or the number of vertices minus 2, so you use the formula, there's 14. So that means I get 14 Neff cones in 3-dimensional space. So now I'm getting, this is sounding interesting, I'm getting a whole bunch of Neff cones. And how are they related? And it turns out that they form a complete fan. They completely fill up 3-dimensional space. And that's called the secondary fan. And one of the reasons that it's complete is because, in fact, it's the normal fan of a polytope. That's called the secondary polytope. So there's actually a polytope that lurks here. And then it turned out in this case, the polytope is called the icosahedron. And just a picture, here are the 14 triangulations. There's the polytope. And so the normal fan of this, the cones, give the 14 Neff cones. So basically, if I take that particular guy, that gives a toric variety. What's its Neff cone? Well, this is a vertex of the polytope. It corresponds to a maximal cone. Remember, you take the cone here, take its dual. That's the Neff cone. So, mind-blowing. But it's even better because, for example, these edges actually mean something. Because here's a Neff cone, there's a Neff cone. That means they share a wall. And when you cross a wall, something happens. And when you look at these 2 triangulations, notice that this one and this one are the same. But on this side, see, I have a little quadrilateral, and there's a diagonal. I've just flipped where the diagonal is. So that flip is what happens when I cross that wall. But for example, like when I look right here, notice that that one and that one are the same here. And this time it's this quadrilateral. So for this one, for these adjacent nef cones, crossing the wall flips that diagonal to that diagonal. And then when I go right here, it turns out it's this middle quadrilateral that when I go here, you see it's the same middle quadrilateral, I just flip which diagonal I use. So for example, if you think about it, here's a polytope where every, I always have 3 facets meeting at a vertex, and that's because there's 3 diagonals I can flip. So I get this wonderful combinatorial description of what's going on. And now it turns out that this Catalan numbers count lots of things, because they have a lot of combinatorial interpretations. And in particular, the Catalan number C4 counts how many ways parentheses can be introduced in a product of 5 things. And it turns out to write down all of that would be pretty hard, so I did something simpler. And so for C4, I count 5 things. And so for C3, how many ways can I put parentheses on 4 things? And here are the ways that I put parentheses on 4 things, and this Catalan number is 5. And so basically, and in this case, you get a similar kind of, in this case it's just a polygon, and then what happens is that when you do something, like for example, I could use the associative law here. I could move, I could move these parentheses to those parentheses. Well, that's an edge, and so it turns out that each of these interprets as one of these ways of doing parentheses, and each edge is just using the associative law. And that's why it's called the associahedron, and that's actually the context in which it was discovered. And so what this means is that when you get into toric geometry, there's some wonderful combinatorics that pops up. But there's other fun stuff that happens. So now let's do our time traveling. So this is 240 years ago, and Bezout wrote his book on the general theory of algebraic equations, 500 pages long. And so we all know that Bezout did Bezout's theorem. Well, of course, the version of Bezout's theorem that we all know was known well before Bezout. For example, Newton knew Bezout's theorem in the plane 100 years before Bezout. And so what Bezout did is he did lots of Bezout theorems. So I'm going to tell you about some of his Bezout theorems. And so he had this elaborate classification of polynomials. And so we take a polynomial of degree t, and here I'm thinking affinely. And so it'll include monomials of degree, so basically all the monomials in here have total degree at most t. We call the polynomial complete when it uses all monomials of degree less than or equal to t. Then he talked about incomplete polynomials that don't use all of them. Now we have our own name for that. We call that sparse polynomials. And so a lot of stuff. And we think sparse polynomials is really hot modern stuff. Well, here's Bezout doing sparse polynomials 240 years ago. And what he did is though he had very structured ways of thinking about sparse polynomials. He didn't take just an arbitrary set of exponents, vectors. He took a very clearly defined one. And so he organized them into various kinds of things, and he had species. And in particular, he had what he called the third species. And so monomial is in the third species. What that means, so that means there's third species defined by these 7 parameters, and the first just bounds the total degree. And so that's saying that I'm going to be using some monomials of degree at most t. But then what are the further restrictions? Well, the A's, they put restrictions on the degree of x, on the degree of y, and the degree of z. So I bound the degree in each variable separately. But then the other thing that he does is that he puts bounds on the degree of each pair of variables. So when I look at just the first 2, x to the k1, y to the k2, that has that degree, puts a bound on that, puts a bound on the first and third, puts a bound on the second and third. And so it turns out that this can happen in quite a different ways. It's sort of, how do the these T's, A's, and B's interact. It can be pretty complex. And what Bezout realized is that basically it was sort of these combinations, because notice I'm taking two ones from the B's, and then the other one is an A with a plus sign. And so you take all those, and it turns out that those can be plus or minus. And so you get basically 8 forms according to this. And Bezout had sort of a Bezout theorem for each one of those. So for example, now let's think in more modern terms. So let's take this one right here, and let's suppose that I'm in the case where all of these are non-negative. That's what he called the first form, and or non-positive rather. So the idea is that because notice that this is a polytope being represented as basically an intersection of half spaces, and and it's obviously a polytope because notice that all the ki's are greater than or equal to 0, and the sum is less than or equal to t. So this is all sitting inside the big simplex of size t, and then so he is absolutely describing a polytope here. And if I take 3 monomials, so his theorem is that if I take 3 polynomials that basically of this particular species, this is the first form of the third species. If you take 3 particular ones, then when you look at the number of solutions, assuming they're generic, it's given by this complicated expression. So that is a result of Bezout. I'd like to say it's a theorem of Bezout, but when you look at Bezout's proof, it's sort of flaky by modern standards. And yet the result is completely correct. Now the way we prove that these days, where we think we do very modern stuff, is that in this case, because these all share the same Newton polytope, it's 3-dimensional, it's just the normalized volume of that polytope, and that's basically the BKK theorem. And when you compute the normalized volume of this polytope, that's the normalized volume. And so here is Bezout computing normalized volumes 240 years ago. Of course, he didn't think at all geometrically. So he didn't think about the polytope, he didn't think about volume. His ways of computing this were vastly different. I mean, they were basically, he did a very elaborate calculus of finite differences. There's sort of Cazul complexes lurking in the background where he has no idea how to say this word exact. And he sort of says, well, there can't be fictitious cancellations. He simply says there can't be. He doesn't prove it, and so he struggles. But he's right. And then there's very few people actually read Bezout, but one person that actually read Bezout was a historian of mathematics, Ervan Penchevra. He was a student of Christian Husserl, and he read Bezout. He read a lot of elimination theory. He wrote this wonderful thesis on sort of the history of elimination theory, and he really tried to understand it. And then he actually wrote another paper trying to see what Bezout actually did, and he actually used BKK and toric geometry to actually prove Bezout's results. And so these are some papers from, or some pictures from Penchevra's paper. So here's the third species first form. And so notice that this sort of facet right here, that's the one about t. That's the one that's putting the total degree. So that's bounding the total degree. And I'm in the first orthon, so that says that all the variables are greater than or equal to 0. And then you see right here, that's bounding the x degree. That's bounding the y degree. That's bounding the z degree. And then right here, I'm bounding the degree of x and z. Here I'm bounding the degree of x and y, and similarly for y and z. So you really get this. And then so here these, there are 8 forms altogether, so these are some of them. But what's interesting, and so notice that I have polytopes. So I have toric varieties. So I have lots of toric varieties. And all of these share the same inner normal fan. So it's the same story as the previous case. So all of these different toric varieties, what I'm doing is I have the exact same set of rays. I'm just hanging cones on them in different ways. And because they have the same rays, they also, and it turns out that, because when I take a point right here, notice the cone, when I look here at that particular vertex, the cone actually just has 3 rays. That means the cone is simplicial. When I take its dual, it's still simplicial. So these actually give simplicial toric varieties. And so what I get is and of course they're projective because they come from polytopes. So I get all these Neff cones that sit in the same space. And so, for example, and it turns out these ones are adjacent. And the way you see they're adjacent is that they're really pretty similar. But something's happening here. So you see right here, I have this configuration, but I cross a wall and it becomes that configuration. And then it turns out going from here to here, the same thing happens. This time it happens right here. So here I have this configuration, I cross a wall, it becomes that configuration. So there's a wall crossing, there's a wall crossing, and then going from here to here, you can see the wall crossing happens there to there. So basically we're looking at a path through the secondary fan based on, polytopes described 240 years ago. So it's just wonderful stuff. And Bezout had Bezout theorems for every one of these, derived very elaborately. That's part of why the book's 500 pages long. And so it's just great. Now the question is, what's lurking in the background? The answer is, there's a lot of stuff lurking in the background. So this is where some of the geometric invariant theory comes from, which is a slightly spiffier way of doing quotients than what I described last week. And so this is what I'm going to describe is going to have the flavor of the quotient construction, but it's existing a bit more generally. And so we have a group. So we have the torus, and we have a subgroup, which is a torus times a finite group. And I want to define a GIT quotient. And it turns out for that you need what's called a linearized line bundle, because the idea is that G acts on my affine space. This is the trivial line bundle over it. And so for the action to lift to this trivial line bundle, I basically have to multiply, and I want it to be linear on this coordinate. It means I just sort of multiply by a character of G. So basically there's a character, so that's what the chi is. It's a character of G. And then it turns out that when you do the stuff about geometric invariant theory, this data determines a set of semi-stable points. And then the semi-stable points depend on the character. And then there's the even nicer stable points. And then what they call the GIT quotient is, and so the idea is that this will be some nice subset of C to the R. And so you take this nice subset, and this is a quotient where you make the quotient pretty much the way I described last week. You cover this with invariant affines and take rings of invariance and stuff like that. And so on this part, so it turns out that on the semi-stable part, you get a good categorical quotient. And then the point is the stable points are much nicer, and there you actually get a geometric quotient. And for example, a lot of the language that I'm using here really arose in the context of geometric invariant theory, a classic book that Mumford wrote in the 1960s. And we'll see a little later that the fact that this is coming from a linearized line bundle with this character chi, that actually guarantees that these guys are quasi-projective. Because remember, I can use the quotient construction to build pretty much any toric variety, including non-projective ones. And so there's a little extra structure here that's actually guaranteed that I'm going to get something quasi-projective. And so the familiar example is, take a polytope, and then I take the normal fan, and so we have the group in the quotient construction. But remember, this group G is basically designed so that its character group is the class group. And then, of course, what does the polytope give us? It gives us this nice ample divisor, and its divisor class is in the class group. Well, that means that's a character. And so that's the point, is that the fact that when I'm doing the quotient construction in the case of coming from a polytope, we have this extra structure of we actually have the character. And then when you look at stuff, when you take the set of cones, because remember that you don't always get a geometric quotient, and but you do get you do get a good categorical quotient. And it turns out the GIT quotient is exactly the toric variety of the normal fan. And what happens, in fact, is that when you look at the semi-stable points, it's exactly this minus the set that we remove in the quotient construction. And then the idea of the stable points is that, and this is something I described very briefly, is that if I look at the subfan consisting of the simplicial cones and do that, then on that part I actually have a geometric quotient. And so basically the stuff that we did in the quotient construction fits in this more general framework of a GIT quotient. Now, I said that these GIT quotients were quasi-projective, and what that means is there's going to be a polyhedron lurking in the background. And so remember, the framework is that we have our group, we have a character, it's character group, and but notice that this group sits inside of C star to the R, so the character group of C star to the R is Z to the R, and so I get a map going the other way in character groups, and so the basis element here gives just a gadget that we call beta I. So we get an interesting collection of characters just from this. Now, if you apply this to the quotient construction, it turns out in the case of the quotient construction, the character group is the class group, and the beta I, so it plays their role, is the divisor classes of the D sub rows. So what we're doing is we're taking this one that we're familiar with and just making it slightly more general. And then, of course, when I take this guy, I get, and it turns out that you can show this map is onto, and then I take the kernel, and that'll just be some sublattice, and then it'll have a dual n, and then it turns out that this map right here is basically just a bunch of it's based out of R linear functionals on M, which means it's based on some elements of capital N. And this is a formula that looks pretty familiar, and what that means is in this very general context, the new I's sort of play the role of the U sub rows, because in our case, this map right here, this was M to the direct sum over sigma 1 into the class group, and this was just the inner product with the U rows. So we're just generalizing that. And so basically, when we have this structure in the case we're used to, it generalizes to the beta I and the nu I, and there's sort of what's called Gale duality lurking here in the background as well. And then what happens is that you define stuff in the usual way, and so and so the idea is that, remember, we have a character here, chi. Well, it's something here is going to map onto it, and so we have something here mapping onto it, and so we have and then we define P sub chi in just the usual typical way, and because that should look very familiar. And again, remember that chi, these guys map to chi, and that's what's giving us this polyhedron. And it turns out that this is a toric variety of a polyhedron, and therefore it's quasi-projective, and that's the stuff we did in chapter 7. And that's part of why we had to do chapter 7, was to lay the groundwork for this stuff that's happening here in chapter 14. And then now we get one of the key ideas that's going to happen, because notice that in this data, the G sort of determines all this stuff. So once I have the G, I get the betas. Doing this, I get the nus. So all that stuff just depends on G. Then the extra data that determines the GIT quotient is the chi. So the game we're going to play is we're going to fix G. That's fixing these guys, and we're going to let the chi vary. Now, what does that mean in terms of the polyhedron? Well, see, I'm keeping the normal directions the same, but because remember, this is a this is sort of a half space. I'm sort of moving the half space. So I'm moving things around back and forth. And so the question is, as I move around, how does this polyhedron behave? And it turns out lots of times the polyhedron behaves very nicely. It's pretty much the same shape. But then if you sort of cross a wall, it'll change shape dramatically. And that's some of the pictures that we were seeing earlier. So let's look at an example. And you have to be pretty, there's all sorts of technicalities. It might not be a lattice polyhedron. You know, it might not have vertices. If it has vertices, they might not be, they might be rational rather than integral. So, there's technicalities you got to smooth out. And also that might not be the facet presentation. And it turns out that what happens is, so you look at, this part, and you look at where equality occurs. Now, in the case that we're familiar with, when I intersect that with P in a facet presentation, that's a facet. But the point is, this might be something lower dimensional. In fact, it might even be empty. And here's an example. If I just took this little group and let all this stuff unfold, turns out that all the relevant chi's sort of lie here. And then if I pick various different chi's, so again, the chi, remember there's the AIs that map to chi. So as I vary chi, I'm varying the AIs. And so for example, in the interior of this first quadrant, what I get is that. And again, as I'm varying the chi's, I'm simply moving these facets around. Because I have an A1 through A4 in this case, and so I'm just I'm moving this one up and down, moving that one, moving that one, moving that one. And then what happens is that if I move here, what happens is the top and the bottom coincide, and I'm just left with the line segment. And then what happens here, there's a couple of ways to think about it, is that because you see I have that bottom facet, but for example, it might be that this guy is moving that way, and so instead of being actual line segments, that. So here I get one of these, we call this a virtual facet in the book. And then what happens here is that the virtual facet moves away. In fact, another way to think about it is think about moving this line here down. As I move it down, the triangle gets narrower and narrower. So as I move it down, I get something like that. As I keep moving it down, I get something like that. And so here I have an empty virtual facet. And what's lurking is that, this, of course, this polytope gives the, in fact, do you recognize what it gives? It gives a Hertzsprung surface, and it's actually H1. And in fact, what you have here is the Neff cone of that Hertzsprung surface. And then what's happening over here is, that just gives P2. Now there the Neff cone is one-dimensional. This cone is two-dimensional. So this isn't really the Neff cone of P2. It's the Neff cone with some extra information. And the extra information is basically how far away is the virtual facet. And so it sort of keeps track of that. So this is sort of an enlarged Neff cone. And then the cone that you're working with is the cone generated by the betas. Because remember, the structure gives a beta, and you always work in the cone generated by the beta. So the secondary cone is, the secondary fan is, its support is just what's generated by the betas. And so this is a very concrete example of a secondary fan. In fact, Hal, I think you drew a picture pretty similar to this in one of your lectures. And the point is that that picture gets reinterpreted in the GIT world as a slightly more sophisticated object. So now let's go back to our favorite toric variety. So we saw this on the very first lecture. And then when I talked about the quotient construction, we saw that I could also do this as a quotient construction, and here this was definitely a good categorical quotient, and and remember that one way to, and the question is where do we get this isomorphism? Well, the idea is we take this Z4 with these coordinates, and I map it to another C4 with these coordinates, and I use this map right here because all these guys are invariant under the group action. And, but then of course, notice that X times Y is Z times W, and so that's where you get, this guy is actually that variety. And again, that was example C in the background lecture I gave last week. And so when you work out the story here, what the G hat is, G, that's just a isomorphic to C star, so you get this. And then what you work out, you can work out the betas, and you can work out the nus. And of course, these nus are the ones that generate that very basic cone I drew that, and that cone that actually gives this toric variety. And it turns out when you work out the secondary fan, and because notice that that's all living in here, and so it's all one-dimensional. So in fact, the secondary fan is slightly boring. It has basically two cones. It has three cones. It has 0. It has this stuff and it has that stuff. So there are really two chambers and one wall. And so the question is, and so in this case, in this situation, for this particular group, when I do the GIT thing, I can take the quotient of this mod G, but for any character. So now what happens? So the question is, how does the GIT thing correspond to this one we did right here? So what's the relation? And it's sort of fun that let's see. Oh yeah. And it's sort of fun to see what's going on. And so it turns out when chi equals 0, it turns out that so notice that here are the nus, and that's the picture we had. And then it turned out here's the dual cone. And then here what I did is I labeled every facet of the dual cone. So that's the first quadrant. This sort of comes out below at an angle. And so each facet I labeled with its normal, with its inner normal. So the inner normal here is going to give that one the inner normal, because the inner normal here, notice, points in the x direction, so that's in the x direction, and so that's what that labeling does. And it turns out when chi equals 0, this is p sub chi, and because it ends up being just the dual cone, and so in this case we actually do just get the toric variety of this cone. So in this case, when chi equals 0, the GIT quotient is exactly the toric variety of this cone, which is the variety of xy minus zw. And so there we understand what's going on. But now what's happening here, well, remember that moving chi means moving the defining equations. And so see, and this is the p chi. And so the idea is that I'm going to take this and I'm going to move the facets. And let's think about moving this facet. And I'm going to move it toward you. And so this facet originally in this one was just right here, completely flat, but I've moved it toward you. And what that does is that alters what was a cone, no longer is a cone, it becomes this polyhedron and picks up this little thing right here. And in particular, notice that nu1 and nu2 sort of share there, and you see that's because right here I've sort of basically added a wall to the cone. So that's the effect that, when I, in a sense, one thing to think about is this is a very non-generic situation. When I make it generic by making it negative, I get something that looks like this. But if turns out when you work out what happens when I make chi positive, you could think about that. Think about taking this face, which would be this one right here, and pushing it this way. And again, this is sort of coming down at an angle, and so you get something that looks like this. So again, all three of these have the same inner normal fan. Or rather, yeah, they all have the same facet normals. But the difference is, notice that this is not a simplicial toric variety. So this is sort of non-generic behavior. So we actually from the GIT point of view, we don't really like this very much. But notice that right here, this, and again, that fan's not simplicial, but notice that right here, you can see the three facets come together at each of the vertices. The vertices correspond to the maximal cones, and you can see that those guys are simplicial. Same game here. And so what I get, my two chambers correspond to these two pictures. Now, if you think back to the two first examples I did, well, in the first example, what did I do? I took a hexagon and I triangulated it. And we saw the basic thing that happened in a flip on an edge is I take a quadrilateral and I just flip the diagonal. Well, notice that that's exactly what's happening here. If I can think of this as a little rectangle, and see, I start with just the bare rectangle, there's a triangulation. Here's the other triangulation. And in fact, basically for the relevant Catalan number here is 2, because there's only 2 of these guys. And so here you can really see sort of crossing the wall, namely going from negative to positive, I cross that wall, and so that just basically flips. But the way it flips is that the flip happens actually in the polyhedron, and notice I go from this configuration to that configuration, and that's exactly the flip you saw happening in the Bezout example. And so, before I presented them as two separate examples, but when you really do this GIT theory, you see them happening simultaneously, that each one explains the other. So again, there's a very rich, so even though this is an incredibly simple example, there's some really rich stuff going on here. Now the next thing I want to talk about is a quite different example, and partially it's, when you work with this stuff, people can present the basic information in more than one way. And I gave an approach where I started with the group G and let everything unwind from that. Sometimes people do a different way. They specify the GIT data using matrices. Because let's take a little exact sequence with matrices A and B. And so B is this guy and A is that guy, and you could easily show that they're actually, it's exact. And it turns out that what's happening, and then this is an example of Gale duality, that basically from this guy, I sort of invent A as the co-kernel. From A, I invent B as the kernel. That's sort of Gale duality. And it turns out that in our GIT language, sort of the rows here are the nus, and the columns here are the betas. So this is simply a different way of presenting the information. Now you might wonder, but where's the group? Because wasn't the group the crucial thing? And the way to remember that is remember that I gave a formula when I talked about the quotient construction for how to construct the group. And the group was basically equations like this, where I used the use of rows here. So those were the equations that I used. And the point is that in this more general context, the nus play the role of the use of rows. And so once you hand me the nus, that's actually enough information to define the group. And so this way of thinking about things relates very nicely to the other ways. And so what we get in this one is we really are in the situation we were before. We have the group defined here. This group, that gives us the nus, that gives us the betas. We're all happy. Now, a way to think about this, so you can see another amazing picture is lurking here, is let's think of this as a configuration of points in three-dimensional space. And so they all lie at height 1. And what it is that I have 5 points, and you can see that the way I've set up the points, when you actually sort of plot them, what you get is a little configuration that looks like this. So it looks like a rectangle, and the 0, 1 is that point right there. So when you go back here, sort of the top 2 and the bottom 2 rows, those give the vertices, and the 0, 1 gives the point in the interior. And so I get that lying at height 1. And so now again, I want to triangulate. But here, I have to actually, in the hexagon case, I could just say triangulate. Here I want to be a little more careful about how I triangulate, because if you think about some of the pictures that Hal drew when we were constructing our non-projective complete toric variety, that was basically a triangulation of a triangle that had this weird cycle structure that ended up completely messing up everything. So if you're going to triangulate, and yet we want GIT quotients to be quasi-projective. So I have to be a little careful about how I triangulate. And the way we triangulate, in this case, it's called a regular triangulation. And so basically what happens is you have these 5 points, and you imagine raising each of the 5 points up a certain distance. And so you have 5 points now in 3-dimensional space. And you take what's called the lower convex hull. So you just sort of look up and sort of see what you get. And then that lower convex hull ends up being a regular triangulation. And for example, it turns out in this particular case, for that collection of 5 points, you get 1, 2, 3, 4, 5 regular triangulations. Now the question is, what happened here? So why does this not contribute to what's going on? And the answer is, remember, I was raising stuff up and then sort of taking this lower convex hull. Well, if I raise this guy up too far, he has nothing to do with the lower convex hull. So the lower convex hull doesn't see this point at all. And so these are cases where I raise this point too much and it contributes nothing. And so then I just, basically I have a rectangle, there's only 2 triangulations. And then here, I've been pretty careful about how I've raised it, and so then I get sort of these ones. And now what's going on, so in this case, what happens is the betas, so this is another secondary fan, and my betas in this case actually span the whole space, so I'm going to get a complete fan in this case. And then of course each one of these, like this one right here, again, that really looks here, that gives a toric variety. This one right here, that gives a toric variety. So I get a bunch of toric varieties, and basically they're quasi-projective because I did a regular triangulation that guarantees quasi-projective. So I'm going to have a nice Neff cone, and in these cases where I use all the rays, I have an actual genuine Neff cone. And again, it's the case of 3 Neff cones in the exact same space, and these are the Neff cones of the corresponding toric varieties. And what happens is so what happens right here? And so this is a wall crossing. So what happens to the toric variety? Well, in the toric variety, here are the 2 toric varieties. So you can see it's exactly, again, one of those flips. They're going from here to here. Basically, I just slightly, so I'm using the exact same rays, but I'm just turning them into cones in a different way. So I just flip this diagonal to that diagonal. So that's what happens here. Right here, I have the same kind of thing, and because here you can see so let's see. So which one is it? It's this upper one right here. When I take that one and flip it, I get that one. So here I have these 2 nice flips. Now what's going on here? Well, again, here, this is not the Neff cone of this object, because you see here these guys have 2-dimensional Neff cones because I'm in basically in 3-dimensional space, and I have 5 rays, so Neff cone lives in 2 dimensions. And but here I only have 4 rays because, like I said, I'm not using that guy. And so the Neff cone's only 1-dimensional. So in this case, again, this is one of these enlarged Neff cones. It's the Neff cone of this. In this case, it's information about how high did I lift that guy. And so again, there's extra information. But it turns out there's still something interesting that happens, because what happens when I cross this wall in terms of the toric varieties? So I have this toric variety, and then I have that toric variety. I've done a blow up. And so that, or going this way, it's a blow down. And so that's the idea, is that when you sort of do this wall crossing game, you can sometimes get flips, sometimes you get blow ups or blow downs, depending on which way you go. And so, like I said, there's a lot of beautiful geometry encoded into the secondary fan. And now to finish off, I want to talk about the minimal model program just a little bit. And so what's a minimal model? And so it's basically, we know most of the words here. So it's a normal Q-Gorenstein projective variety. So, Gorenstein means that the, canonical class is a Cartier. So what does Q-Gorenstein mean? It means some multiple is Cartier. So we know what that means. We know what Kx is. We know what Neff means. And so what we don't know are terminal singularities. And that's because we haven't done chapter 11. And if you do chapter 11, they talk about terminal singularities. And so these are the kind of singularities that people have figured out, if you're going to have a minimal model of a variety in high dimension, it turned out for surfaces, minimal models tend to be smooth, or are smooth. In higher dimensions, minimal models sometimes have to have singularities, and that's the allowable kind of singularities. It turns out that in dimension 2, terminal singularities mean smooth. And so you only really see actual terminal singularities in dimension 3 and higher. And so what happens if K is not Neff? Well, in this case, because remember, you test Neffness by taking the intersection with all irreducible curves, and if I always get greater than or equal to 0, I'm Neff. So if I'm not Neff, I've got to be a curve here, and with -1, and this is the side of the Mori cone that actually has a nice structure. That's Mori's big theorem, and so the idea is that if it has a nice structure, you can take it to basically be an edge of a ray of the cone. It's a so-called extremal ray. And then an extremal ray actually gives an extremal, what's called an extremal contraction. And it can be, and there's various names to go. It might be a Mori fibration. So you actually map to something of lower dimension. It might be a contraction of a divisor. So that's a blow down. And it might be what's called a small contraction, and that's where the exceptional locus has codimension greater than or equal to 2. And very super naively, with one big lie embedded in it, is that the strategy of the minimal model program is, well, I'm not Neff, I have an extremal ray, I use an extremal contraction, and I keep doing that until I arrive at a minimal model. Now the twist is that I lied outrageously, because small contractions actually leave the category of varieties we want to be in. So when you do a small contraction, we're going to need to do something different. Because basically small contractions will, the image space will violate this terminal singularity restrictions. So let's do an example. And so basically the idea is you can do the minimal model program in the toric varieties. Now what happens is that, if you think about it, the canonical divisor of a toric variety is minus the sum of all the divisors. That minus means you aren't going to make this guy ample or Neff. And so what happens is that the minimal model program for toric varieties is always going to end up at a point. And so in one sense it's uninteresting, but on the other hand you can see some of the basic behavior by just observing this. And so here's a nice fan, gives a smooth toric surface, and it turns out that each of these walls gives a curve, and you can do the calculations very easily, and it turns out that you get this, and so it turns out that we have some extremal rays and of the Mori cone, and it turns out that one hits with 0 and the other two hit with -1. So I can use basically either this guy or that guy to get a extremal contraction. And so let's see what happens when I use tau 3. And the crucial thing that you do so I basically want to kill this guy. That's what a Mori contraction does, but I have to kill everybody who's numerically equivalent to it too. And in that case, that's no big deal, because when I kill that guy, I've simply removed that cone, and it turns out that this guy's still smooth, and so I've just blown down a divisor, and so I now have, so now you ignore the red, and I now have a slightly smaller one. And then in this case, so I just have, so now X prime is where I've removed the red, and so, and it turns out that the Mori cone of this smaller thing, basically these two guys generate the same thing, and then also that, so those two and that basically generate the Mori cone. It's a two-dimensional Mori cone now, and it turns out they both have negative intersection with the canonical class. And so I get two of my extremal contractions, but they behave differently. Because when I take this guy and remove it, because so I'm going to take that extremal contraction, because that's an extremal ray that has the negative self-intersection. Well, the point is, I have to remove that one, and I remove that one, and I collapse the cones. So notice what I get when I take these two cones and collapse them. I get a cone that's not strongly convex, and similarly when I remove that one, I get the other side, and so that's a degenerate fan. And remember, in a degenerate fan, I have to collapse the maximal subspace to a point, end up with the just P1, fan for P1, and so in this case, I get a Mori fibration from X prime to just P1. Whereas if I you remove this guy, that's the only one I have to remove, and then I get this cone, that cone, that cone, and I get another divisorial contraction to just P2. And so you can see how you can actually do this in the toric context. And you see how you can witness some of the basic things. But you can also witness one of these small contraction things. Because remember I said that there was a problem with the small contractions. And so in this case, when I basically, so suppose that was my X, that's the only, remember this is, I am doing a slightly tweaked version of the minimal model program because I'm no longer projective, but in this case, that's the only interior wall, so that gives a complete curve, and that generates the Mori cone, and when I try to make the small contraction, well, that means I remove it and collect it. I get that. There's our favorite toric variety appearing yet again. But it turns out that this is too singular for the minimal model program. So what the minimal model program does is they use a flip, and that's where they go to an adjacent Neff cone in the secondary fan. And they go to an adjacent Neff cone, and so they take this and replace it with that. And the idea is that if you're in a situation where things work nicely, this has better properties. And so the actual minimal model program says that when you do a small contraction, you don't use this guy, you instead do a flip. And then what happens is that in the minimal model program, then you have a series of either you have a Mori fibration, which takes you to something lower dimensional. That's easy because you assume by induction lower dimensions, or you do a divisorial contraction. But notice that you can only do finitely many of those, because every time you contract a divisor, that basically shrinks the size of the class group. And so you can only do that finitely many times. So the real problem is the termination of flips. And then what happens is that in the toric case, what we're doing is that when we do a flip, we're basically working in the secondary fan. And so so in this case, we have a really nice structure of what's going on. And then what you have to do is prove termination of flips. And what happens is that in the toric case, there's still work you got to prove, but the idea of what's happening here is that things work because the secondary fan has only finitely many cones. And so when I go from one Neff cone, when I do a flip to another Neff cone, that can only really happen finitely many times. and because you can prove that you can't have cycles. And so that's roughly speaking how things work. And so the full minimal model program is deep, hard algebraic geometry. I mean, like one of the people that just won the Fields Medal was one of the people that made the big progress on the minimal model program. Maury won a Fields Medal for his contributions to the minimal model program. The Toric one is vastly simpler, but it does give you some nice insight into what's going on in general. And so, for once, I finished 5 minutes early, so we're done. So any questions?
I have a very naive question. Go back to slide 8.
So let's see.
Yeah, so this is an extremely naive question. If I look at this picture, or if I take one of these pictures and I can imagine I'm just looking at the plane, so I kind of project this down onto a plane, it looks like I'm looking at
it's quite possible. And so do some of these species thingies of the zoo have a tropical interpretation? That would be a really cool thing to think about. So the answer is, I have no idea, but that might be fun to think about. Does this have a tropical meaning, and can you then use tropical methods to get some of the zoo's results? I have no idea. If I knew more, I'm going the wrong way. I apologize. Yeah, so. Yeah, so the answer is I have no idea, because the cluster algebras are these really cool gadgets that you build, and I've heard probably 6 talks on cluster algebras, and I confess that I still have no idea what's really going on. Even though I also am firmly convinced they are worth studying, and there's some really cool stuff. So it's possible that there is something going on there. Because there are things called mutations that people tell me about. Maybe these are related to mutations. Yeah. So the answer is possibly yes, but I am not the right person to ask. So let's take maybe about 2-minute break and then turn the floor over to Lynn.
Go run around, wake up, and drink your coffee before you come.